Assalamu alaikum Pakistan. क्या हाल है आप लोगों के? My name is Salman Iqbal. I'm an MLOps engineer at Appvia and Kubernetes instructor at LearnK8. Welcome to KCD Pakistan. It's been a long time coming. Special shout out to Saim Safta, the man. None of this would have been possible without him. So thank you, Saim. I'm very happy and I'm very proud to call you my brother and my friend. Appreciate all the effort you've been doing to put this event together and flying the flag of cloud native in Pakistan. I've got a few things to talk to you about today. I hope it's going to be a good one. I hope you enjoy it. We're going to be talking about how do we scale websites in Kubernetes. We'll talk a little bit about what services are. So let's get started. So imagine you have a website. We have a very simple website here. It's just a red page. And imagine there's some traffic going to it and people are getting served happily and everything is good. What if at some point a lot of users start visiting that website? What could happen is your website might not be able to handle the traffic that's coming in. So what we really want to do is, if there's a lot of traffic, we want to scale up so all of the traffic can be handled correctly. And that's what we're going to talk about in this talk. How can we automatically scale our resources in Kubernetes to handle this use case so that we can scale out and serve all the traffic? As I said before, my name is Salman Iqbal, instructor at LearnK8 and MLOps engineer at Appvia. You can find me on Twitter at Salman Iqbal, and you can subscribe to my channel, Salman Iqbal as well. But before I start, really, I'm going to iterate again. Gotta give a massive shout out to Saim Safta, the man who goes by the name of Cloud Native Boy on Twitter. He's not only organizing this conference, he's done a lot. Cloud Native FM and all the talks that are online. So definitely check him out. Before I start, I would like to thank Daniela Blincic, my friend and my colleague at LearnK8, who helped me put this together, and simply just being a legend. And also Bart Farrell, man of many talents and also a co-organizer. Definitely check him out, show him some love. Let me just explain to you a couple of terms that you're going to be coming across. Imagine this is the website that we're deploying, right? So that's the website, the static red page that's running inside the Kubernetes cluster. A user can visit the website by going directly to the app. Sometimes, as you saw earlier on, we might want to scale up. We might want to have multiple instances of the application running. So if we have multiple instances of the application running, there is no easy way to distribute the traffic to both. How do you route the traffic to both? Well, what we could do is we could use a load balancer, and it's designed to evenly distribute the traffic to both instances, right? So this is what we do right now. We can put in a load balancer, request will come in, it'll distribute the traffic to both. And what you might do is you might run multiple applications. But here's the thing though. How do you distribute the traffic based on the request coming in? Somebody might send a request to this red page. Let's say they go to example.com/red. If that's the case, we want to send them to the red page. Or if they do example.com/beige, we want to send them to the beige application that's running in. So in what we can do is we can add in another load balancer on top. And this load balancer could distribute the traffic to the internal load balancers and the apps themselves. So what we got here is a few things. We have our applications running at the bottom, then we have the internal load balancers, and then what we have is external load balancers. When Kubernetes, the internal load balancer is called a service, and the external load balancer is called an ingress. That's what it's called. And the applications that are running inside the container, they're not called apps or containers. Instead, they're called pods. And the reason why they're called pods is because inside a pod, you could have one or many containers. So starting from the bottom, we have pods, we have services, and we have ingresses. Of course, there's many other resources in Kubernetes, but we only going to focus on these things. Usually, when we do deploy something to our Kubernetes cluster, a pod that we want to deploy to a Kubernetes cluster, we usually deploy using a deployment rather than a pod itself. So how do we actually interact with a cluster? How do we create these resources? Well, one of the ways of creating resources is using the command line tool called kubectl. And what you usually do is this, what you'll see in the demo, is you use the command line tool, you write some configuration file, and you will send that to the cluster. And that would create you the resources. You might say, deploy me 2 replicas of an application that you want to deploy. And that request is going to be received by a component inside Kubernetes, which is called a control plane. And control plane has a number of other components inside. Inside your cluster itself, on the worker nodes, you will have 2 pods which will appear. And what happens is that each of the pods get an IP address. You need to be able to send traffic to it, right? So how do I send traffic to it? Well, each of the pods gets an IP address. And then we want to make these pods discoverable so we can send the traffic to it from outside of the cluster. Or it could be from inside the cluster, another component wants to send the request to this component. So we're going to create what's known as a service. And the reason why we have a service is because imagine you have these pods with IP addresses. And these pods could disappear at any moment. They could get killed, they could crash themselves, and if they're deployed using a deployment, Kubernetes will bring it back up. So the point of having a service is that it acts as an abstraction layer on top of the pods that are running. So instead of pod making a request to another pod, a pod would make a request to the service, and the service will keep track of where all the pods are running and how many pods there are. And then it would pick a pod based on the logic that it's written in, kind of like a load balancer, and then we'll distribute the traffic to that pod. And that is one of the reasons why we have a service. There's different types of services in Kubernetes, and they'll behave slightly differently. One of the most basic service is called a headless service. It's a basic building block of all other services. Really, a headless service gives you an IP address of the pod. That's all it is. But headless has some limitations. It's not quite good at load balancing. So this is where we have another service which extends the headless service called a cluster IP service. And cluster IP is a default service. If you create a service inside Kubernetes and you do not define which type of service it is, Kubernetes will create a cluster IP service. It extends headless service and provides a service which is closer to a load balancer. And these two services that you've seen so far can only be used internally. We can't access the pods associated to these services from outside of the cluster. For that, we need some services that can be exposed externally. And this is where the node port service comes in. This is used to expose services to outside of the cluster. It extends the cluster IP service, and node port can be used to expose the pod to external traffic. All it does is that it exposes a port on each of the nodes so the pod can be accessed from the outside traffic. What you really need is an actual load balancer to put on top of those nodes. So this is the reason why this load balancer service exists. The load balancer service. If you create a service of type load balancer, it will create your load balancer in the cloud and attach it to all the nodes. There's a few gotchas. A load balancer is automatically provisioned and is attached to the node ports. And it doesn't work out of the box unless your cloud provider or your infrastructure team adds it. And also, it could be a little bit expensive. And load balancer and node port are useful if you wish to expose services that use layer 4, TCP and UDP. They don't work with HTTP requests. Imagine you want to route the traffic in your cluster based on, let's say, a domain name or a path. It's quite common to have a cluster with multiple components running. You might want to have a way to route traffic to each of the components based on a path. Or you could use the same logic to host several websites under the same cluster and decide to route the traffic based on the domain name. A service can't help us there. And this is where the Ingress comes in. Ingress understands how to deal with this. So we can forward the requests to the correct application based on paths. We can ingest a large number of requests while keeping a low latency. We can also use SSL terminations, and we can apply policies such as rate limiting and authentication. So far, the Ingress has been shown as a black bar. What is it really? Well, it turns out Ingress is just a regular deployment plus a service. It's usually node port or load balancer. There's two parts to Ingress. There is this Ingress controller, and then there's the Ingress manifest, the rules that define how the traffic should be routed. This is what the Ingress manifest looks like, the YAML file. I'm sure you might have seen these before. Well, if you have, at the very top, you have this API version, what kind of resource it is, but the most important bit in here is the rules bit. So the HTTP rules that we're showing you here. What we're saying is if somebody sends a request to this Ingress, forward it to the service front end on a specific port, because that's what So we take this YAML file and we submit that to the Kubernetes cluster. The Ingress itself is a programmable router. So when it starts or when something changes inside etcd, it connects to the control plane and it retrieves all the ingress rules that were written. For example, what we're saying here is if request goes to the first ingress 1, the request should be forwarded to the front-end service. And then the front-end service will decide which pod needs to be sent to. So here's the thing though. We are running a website, the red one at the bottom. All the requests are coming from outside of the cluster and has to go to the ingress pod first, which then forwards it to the right service, etc. and etc. Now imagine if you receive a ton of requests and your pod gets overwhelmed with the requests that are coming, it can't deal with it. What do? Well, this is the point. What we'd like to do is increase the number of instances of ingress controllers so we can handle the incoming traffic. We can do that. As I said before, ingress is a normal deployment, right? This is what a deployment file will look like. But the important thing in here is the replica field. How many replicas you'd like to run. Currently, it only has one replica. In this case, what we could do is open the deployment file and increase the number of replicas from 1 to 3 and resubmit that to the cluster. And apply to the cluster, and the replicas will increase, the traffic will be served. Okay, no problem whatsoever, because that's the first entry point. But it doesn't seem very efficient to open a deployment file and change it to number 3 replicas and submit it. Imagine if that happens at 3 a.m. in the morning. That's a bit of a problem. What we do need is something that can scale our pods automatically, something that can watch our cluster, and if there's a need, only then scale it. And this is where horizontal pod autoscaler comes in. Horizontal pod autoscaler is a resource in Kubernetes. It's a means to respond to an increased load to deploy more pods of that kind. So here's the thing though. This is what we're going to do. This is what you're going to look at. We'll show you in a second. We have this deployment file and we have a bunch of ingresses that are running. And then we have horizontal pod autoscaler on the right. But how does the horizontal pod scaler increase the number of replicas? Well, what it should do is query for metrics. It should look for something. It should look for a metric, maybe number of active connections. And then based on the criteria that you wrote, maybe scale out, adjust the deployment automatically so we don't have to do it ourselves. And this is what the horizontal pod autoscaler does. It'll increase the number of replicas. So as you saw, it just added another instance, or reduce the number of requests. So what do we need? Well, we need a way to be able to expose the metrics that we want to collect, take that metric and store it. And then what we want to do is eventually is trigger an autoscaling. In our case, Nginx already has some metrics. You can have just listed some of these out. And one of them happened to be is active connections inside that pod. What about the second part, which was collection of metrics? So how can Kubernetes help us with that? There's something called a metric server that collects resource metrics from the pods. It does it via kubelet, but basically it collects metrics. And then it exposes it to things like horizontal pod autoscaler. And this is where we can use an open source project called Prometheus. It's a great monitoring system. We can use Prometheus to collect those metrics and store them. So we got the two things. We can expose the metrics and we can collect and store them, because that's what Prometheus does. That's what Prometheus does. But the last thing, the last piece of the puzzle, is something that can scale things based on requests coming in. And this is where this open source project called Kada comes in. Kubernetes-based event-driven autoscaler. It lets us drive the autoscaling of a Kubernetes workload based on a number of events, such as the custom metrics that we're scraping, breaching a specified threshold, like what we just talked about, number of active connections, or when there's let's say a message in a Kafka queue. It's a great project. You should definitely check it out. It works alongside the standard Kubernetes components, such as a horizontal pod autoscaler, so it feeds the information to the pod autoscaler, and it can also extend the functionality without overwriting or duplication. So, a lot of talk there. Let's have a look at the demo. We'll need a cluster to be able to run it. In our case, we'll have a Minikube cluster. Then we need to have an ingress. And then we're going to have Prometheus and Kada installed on the cluster. And then we also need a way to generate some fake load so we can test it. And then based on that load, we want to auto-scale the ingress. And that is what we're going to see in the next few minutes. What you see here is a Minikube cluster has been set up and it's up and running. Instead of showing you a kubectl get pods, what I have is a dashboard on your bottom left, which shows all the pods in the cluster. Currently, you can see kube system pods, and this is what we're going to use to see when the Ingress pods scale up. Now it's time to deploy our pod, which is this from Stefan Prodan. It's a simple pod that will run in a cluster, and we have a service to go with it. Let's deploy to our cluster using kubectl apply -f deployment.yaml file, and within a few seconds, we'll have a pod up and running. Now it's time to install Ingress, Nginx Ingress onto our cluster using Helm, the package manager. This will install the Ingress controller inside the Kubernetes cluster. Once it's installed, we can also apply the Kubernetes configuration for Ingress, the exact manifest. The rule that says, if I send a request to example.com, send it to the service that belongs to the pod we've just deployed. So let's check if what we deployed so far is even working. We can use the minikube service command to go directly to that service. We can get this address and hit that directly. That will show us if the website is working. And here it is, it's working. We can access the website that's running inside the container. Let us also deploy the Ingress that we wrote earlier on. So when we deploy it, we'll have the rules in there. Once it's there, we can go ahead and look at the service endpoint for the Ingress controller. If we send a request to that with the header of example.com, we should see the same content returned back in the request as we saw in the browser. Let's also install Prometheus on our cluster using Helm chart so we can script the metrics and feed them to the metric server. Once Prometheus is installed on the cluster, we can open the dashboard like you see in front of you, which we'll be using to run some queries in real time and see what's happening with the metrics that we are trying to monitor. And now we'll use another open source tool called Locust, which we'll use to generate load for our. Here it is. You can see the Locust dashboard on your right. We can set number of users, the spawn rate, and the host that we want to hit, the Ingress host. And top left, you have the Prometheus dashboard, which shows you the number of Nginx active connections inside. And at the bottom left, you can see the dashboard that we got with the pods that are running. And there is one Nginx controller running inside. And now we've spun up a number of loads. Now we've sent. And right now we're sending all those requests in Locust to our Ingress. So the requests are getting sent to the pod itself. But currently there is only one Nginx Ingress. And you can see the response time will start going down slowly. And the number of users are increasing. The number of requests are also increasing. So this is the time where we might need to do something with scaling. Now let's install Kada using Helm chart. Once Kada is in, we can write Kada configuration to be able to do our auto scaling. So let's have a look at how do we actually do scaling. We use what's known as a scaled object, which targets a deployment, and we tell it which deployment. This is the Nginx Ingress deployment we're targeting, and we tell it what kind of replicas we want in it, but more importantly, we tell it the triggers. What is a trigger? It's a Prometheus trigger. We're taking the metrics from Prometheus, and that is the metric name is number of active connections. If that goes over 100, scale up. Let's apply to the cluster, and let's hop back our dashboard and see all those pods spin up and the number of requests going down. How about that? There you have it, people. You see to your bottom left, we got number of Ingress pods spinning up, trying to catch up with the number of requests because it's going above the threshold that we have defined. We'll see a few more spin up at this time. This is actually, Kada is actually feeding in to horizontal pod autoscaler. It's actually updating the deployment of the Ingress. Let's have a quick look at the Nginx deployment. That has been auto-scaled. First it was running as one pod, now it's gone up to 16 and there's more pods coming up, which is feeding into the horizontal pod autoscaler. So all of this is happening automatically. We didn't set that up. So you've seen today how you can use a metric, scrape it out, feed it to the horizontal pod autoscaler using Kada based on a given threshold that you defined. Good stuff. As now you can see on the right in the middle, the response time is also going down. Well, there we are. That's the end of the demo. Hope that all made sense to you. Hope you enjoyed the demo and understood some of the things that we were talking about. If you have any questions, feel free to reach out to me on Twitter at Salman Iqbal. Subscribe to my channel. Again, a massive thanks to Simon Safdar and Bart for putting all of this together. This has been a great event. Hope you enjoy the rest of the day. And until next time, Khuda Hafiz.